lecture video for January 13th through the 14th. Let's go ahead and get started, get those notes out. Goal for today is to be able to identify the starting value and rate of change given a table, pattern, or graph. Why are we doing this? So we can begin to write equations for linear relationships. All right, so we need to know what rate of change is, sometimes abbreviated ROC. Rate of change is the slope, which we represent often with the letter m. And then this formula is really useful, rise over run. So make sure you've got all three of these representations for rate of change written down. So on a graph, we can find the rate of change by building these things that we call slope triangles. Triangles that connect 2 points on a line by traveling along the grid lines, forming a right angle. So instead of going straight from this point to this point, you could go straight right and then straight up. Well, the lengths of these lines directly tell us rise over run. And if we're going to the right, it's positive. If we're going up, it's positive. If we're ever going to the left, it's negative. If we're ever going down, it's negative. So I'm traveling from here to here, but I'm going along these dotted lines. I go right 2, then up 1, 2, 3, 4. So the rise over run of this, well, the 4 is the rise, the 2 is the run. The rise over run of that first line is 4 over 2, which equals 2. Let's put a little 2 right there. All right, for our next line, I'm going to run 4, then rise 1, 2, 3, 4. 4 over 4 can be simplified to be a 1. Put a little 1 there. And then for this one, I run 4 and rise 2. 2 over 4 equals 1/2. So the slope here is 1/2. So you might notice that larger slopes are steeper. This line is steeper than this one. If I was to actually try to walk along this line, it'd be a lot harder because I'm going uphill much faster than this one. All right, does it matter how you draw the slope triangles? Here we see 4 different slope triangles for the same one. Let's calculate the slope for each of these slope triangles and see if it matters how we draw that slope triangle. All right, for this one, I go down 1, 2, 3, 4, so that's a -4, and then over 4. So rise over a -4 over 4 equals -1. All right, so using the purple triangle, I get a slope of -1. Let's try the blue one. This one goes down 1, 2, 3, 4, 5, but then runs 1, 2, 3, 4, 5. Rise over run is -5 over 5, but again, that simplifies to be just -1. All right, here we've got another -4, 4, 1. This one will also give us a slope of -1. And then with the orange one, it goes down, well, it's at 8 and goes all the way down to 4, so it goes down 12, but then also runs 12. So another way that we get -1 for the slope. So to answer the question, does it matter how you draw the slope triangles? No. As long as you're connecting 2 points with a right angle, you'll always get the same slope. All right, now you try. Add this one to your notes. Tell me what the slope is. All right, so here we go down 1, 2, 3, 4. So down 4, we run 1, 2. Rise over run is -4 over 2 equals -2 when simplified. All right, sometimes we're only given 2 points, but we can still use the slope triangle to get that. The points are 1, 5 and -3, 3. Let's practice plotting these real quick. To plot the point 1, 5, I always start with my pencil at the origin. The first number tells me to go right 1, and then the next number tells me to go up 5. Now let's plot -3, -3. Again, I'm at the origin. -3 means left 3. Another -3 means down 3. So I'm down here. I can connect these up with a straight line, but then also create a slope triangle where I go along the grid lines, make a right angle, go straight over until I'm right underneath it, then straight up. And now I've got my slope triangle. I can calculate the slope. At the bottom here, I run 1, 2, 3, 4. And on the side here, I rise 1, 2, 3, 4, 5, 6, 7, 8. So rise over run becomes 8 over 4, becomes 2. All right, if it's an equation, the rate of change is just the number in front of x. So here our rate of change, we can start calling that m equals 7 or m equals 1/2. What do we do when there's no x? In that case, m is equal to 0. All right, here's 3 more for you to try. Tell me what the rate of change is for each of these. All right, first one is m equals -6. Next one is m equals 1/3. And then with just y equals 1, this is the case where we get m equals 0. All right, now let's talk about tables a little bit. I want you to copy down this table and make 2 mathematical observations. All right, one of the observations you could have made is that the x values are increasing by 1 each time. Another observation you can make is that the y values are increasing by 4 each time. This is equivalent to our rise, and this is equivalent to our run of the table. So rise over run becomes 4 over 1 equals 4. The slope of this table is 4. All right, another observation is that we have a 6 across from 0. This is going to be the next thing we focus on, which is starting value. Starting value is going to be the number across from 0. All right, so we'll label that as m. This we can start labeling as b. All right, what is the rate of change in starting value for this table? So this is our rise. This is our run. So rise over run equals 3 over 1 equals 3. Starting value, I just told you it's the number across from 0. So this is our b value. We're going to start using b for starting value. Yeah, and I think we're ready to do this. Let's start writing this into an equation. The equation for a linear relationship is y equals mx plus b. Here we can fill in a 3 for m and a 9 for b. The equation of this table would be y equals 3x plus 9. Okay, what is the rate of change in starting value for this graph? Again, I'll use a slope triangle to establish rate of change. Here, let me draw that better. I run 1 and rise 3. So rise over run becomes 3 over 1 becomes 3 for my m. And then for starting value of a graph, you see where does it cross the y-axis. This line crosses the y-axis at 2. So that's my b value. And again, let's keep practicing plugging this into y equals mx plus b. The equation of this line would be y equals 3x plus 2. What is the rate of change in starting value for this pattern? So the b value, the starting value, is how many blocks are in the very first shape. Here it's 1, 2, 3, 4, 5, 6. M is how much we are adding each time. You can see that to go from this pattern to this pattern, we add 4 more blocks across the bottom. Same thing here, we're adding 4. That gives us an m value of 4. We can plug it into our equation and get that the equation for this pattern is y equals 4x plus 6. All right. So now these next come from a worksheet that is on the extra stuff calendar. You can just take notes on it here or print off that worksheet if you really want to. I would recommend just trying to take the most important notes into your own notebook instead of printing this one off. All right, so what is a linear relationship? A linear relation is a relationship between two variables that appears as a straight line when represented on the coordinate plane. Most often, those variables are x and y. That whole thing is pretty important. You might want to copy that down verbatim. A linear relation also has a degree of blank. The degree is 1. This means the highest exponent on any variable in the relation is 1. And I bet you can figure out that if it's degree 2, the biggest exponent's a 2. If it's a degree 3, the biggest exponent is a 3. All right, so from a starting point, Mr. Smith runs 2 meters every second. Complete a table of values for the scenario, then draw a graph of the scenario with appropriate labels. So what 2 things do we want to compare here? Probably time and distance, because those are the 2 things that are changing in this problem. So we'll just do time as measured in seconds. and distance as measured in meters. Now from a starting point, so at 0 seconds, he's traveled 0 meters. He then runs 2 meters every second. That 2 meters, that is now our slope. That is how quickly our distance is changing. So after 1 second, he's ran 2 meters. After 2 seconds, he's ran 4, 3, 6, 4, 8. 5 seconds, he's run 10 meters. Now we can turn these into ordered pairs and plot them. Just treat this as the x, this is the y, so this is 0, 0 would be this point right here. 1, 2 would be this point right here. 2, 4 would be right here, and so on. As you go, you might realize you can get from one point to the next by just moving over 1 and up 2 from the previous point. That's because the slope is 2. All right, and this would be totally appropriate to connect these with a line because he does pass through all those intermediate points as he's running. In the scenario above, this is a linear relationship between two variables, time, represented by x, and distance, represented by y. As a general rule, measures of time can usually be represented on the x-axis. That's a pretty hard and fast rule, is that if one of your variables is time, you pretty much always want to do it on the x-axis. All right. A Sea-Doo rental agency charges $100 as a flat rate and $50 for every hour rented. Complete a table of values for this scenario, then draw a graph of the scenario with appropriate labels. All right, so our x is going to be time again. This time maybe measured in hours. And our y value is going to be cost as measured in dollars. All right, if you rent it, but then you return it right away, so you rent it for 0 hours, you still have to pay $100. That's what's meant by a flat rate, is that it doesn't depend on the time. So even if you check it out and immediately check it back in, they're still going to charge you $100 for checking it out. So you might as well use it. If you use it for 1 hour, you'll pay $50 for that hour plus the $100 originally for $150. Now we see that our slope here is 50 because each hour costs 50, so it makes sense that this would be going up by 50s over here. 2 hours would cost 200, 3 hours would cost 250, 4 hours would cost 300, 5 hours would cost 350. What's the initial value of this relation? 100, because that's the number across from 0. What's the rate of change? 50, because we're going up by 50s on this side while we're going up by only 1s on this side. 50 divided by 1 is just 50. All right, now let's plot this. So at 0, we're up at 100. At 1, we're at 150. And then you can find the pattern that we're going over 1, up 5. So over 1, up 1, 2, 3, 4, 5. And then keep that going. One, 2, 3, 4, 5. And there's our graph. Now, we don't know what would happen if we brought it back at the 30-minute mark. We would probably be rounded up. So maybe we just want to leave this as dots and not connect it with a line because we don't know if they round up or down or if they charge partial amounts. So, it could be like a staircase like this. The lines could be on the other side, or it could still be connected with a straight line. So I'll just leave it as dots. All right. The following graphs show Mr. Shaw's bank account balance in dollars as time passes in weeks. For each of the graphs, determine the initial value and rate of change. So initial value, where we cross the x-axis. This one, it looks like it crosses at 50. Rate of change, we can do a little slope triangle. Just go up to the next point that it hits. I go over 1, and then I go up 1, 2, 3, 4, 5 boxes, but that is actually 50 because this is counting by tens. So the rate of change is also 50, rise over run. Here, it looks like he starts at 350. And then this one's going down. And here, this, actually this one, I didn't look close enough at those numbers. That's a 1 over there. So this is only a 0.5. 50 divided by 0.5. This one's going up by 100. I assume the boxes were 1 on the bottom, but they were not. They were only 0.5s. All right, here I go a full 1 over, and then I go, that looks like 10 down. So negative 10 over 1 would be negative 10. On the graph, the initial value is the point where the linear relation crosses the y-axis. A positive rate of change goes up. From left to right, a negative rate of change goes down. From left to right. All right, let's start with a verbal description, and then we'll get the equation, ordered pairs, graph, table, and we'll even talk about what a map looks like. All right, so the output is equal to 7 less than twice the input. So whatever we're multiplying by, that's going to be our slope. If we have anything that's like constant, this is going to be our y-intercept. Put that together, we get the equation y equals 2x minus 7. Now let's apply that to some different inputs. So 2 times 0 minus 7 would be negative 7. And then as we go increase, we'll go up by 2, so this would be a negative 5, negative 3, negative 1, 1. Again, let's double check with 4. 7 less than twice the input. So twice 4 is 8. 7 less than that is 1. All right, we can fill in some of those into this table. So negative 7, negative 5, negative 3. But now we can count backwards to get negative 1, which would be negative 9 by using that same pattern that we're decreasing by 2's going to the right. So we can also increase by 2's going to the left. We can plot those points. 0, negative 7 would be right there. And then the slope of 2, we can get the rest of our points by just going over 1, up 2, all the way across our graph. All right. This one we could connect with a line because you can do twice of a decimal and subtract 7 from it, and that still makes sense. And then a map, it's very similar to ordered pairs, but you actually draw an arrow connecting the input to the output. And it's not very useful unless you're trying to think through almost like proofs and stuff, where you need to prove that everything is connected in certain ways. So we don't talk about maps very often, but the arrows are kind of nice. It clearly shows what our inputs are and what our outputs are. All right. We'll call that good for this lecture video. I'll embed a few more for you to try here, and have a good rest of your day.